Hello everyone, I'm Mahnur and today we will be starting off with the new chapter of AS level physics, which is dynamics. Now before I start diving into this chapter specifically, we should first remind ourselves of all that we have covered up to this point in physics. Now before this point we have discussed all of the details within kinematics, right? And in kinematics, if we recall, we had basically studied the description of motion and how we can do it both qualitatively through graphs and quantitatively through equations, right? Now, when it comes to dynamics, it might seem like we're going into an entirely separate chapter, but I don't really want you to think of it as being too independent from kinematics, but rather think of it as an extension of kinematics. So, take it this way. Where in kinematics we were focusing on description of motion, in dynamics we will be talking about factors that affect motion. So we're still in the realm of studying motion, it's just that now we have stepped away from studying different types of motion and now focusing more on how we can create effects within motion. So now it's an important point to understand basically what does it mean to affect motion. In other words, how can you even picture someone affecting motion to begin with? Well, in our everyday life, we can think of very normal examples in ways we can change or create some kind of an effect on motion. You could take a car and speed it up. You could take the same car and perhaps slow it down. Or you could encounter a turn, let's say, and then change the car's direction, right? So there's a multitude of ways you can create an effect in some kind of motion of any kind of object, right? So in that case, affecting motion really isn't all that new to us. So after having studied how to describe motion, what are we doing now? We are focusing on factors that affect motion. Before we even dive into those factors, it's important to raise the question of what is it that's causing this effect in motion to begin with? That special something is what we call a force. So in short, it's a force that is ultimately affecting motion in one of many ways. Let us first now describe what a force is, and let me write it out here as well. Consider a force as a push or a pull that affects motion. And since it's a physical quantity, it will have its own SI unit of newtons, given the letter capital N. Now, like I just mentioned already, a force is something that is affecting motion. So if let's say we have a box over here and you have Tufi standing here, and I ask Tufi to please apply, let's say, a 10 Newton force to this object. Now, the first question that Tufi will ask is, where do I apply this force? Because if you think about it, if you're asked to change motion in some way, in this specific case, if Tufi is asked to push this box, it's important for us to basically instruct him on where do we apply this force. Where do you want this motion to be affected? Do you want this motion to be affected towards the right, towards the left, up, down, in what direction, right? So clearly, when it comes to a force, a magnitude is not enough. You need a magnitude and a direction, which then specifies the fact that a force is basically a vector quantity. And when we consider a force as a vector quantity, it becomes really important for us to basically write down or describe forces not just numerically but also diagrammatically. And the approach that we'll be taking for the most part is going to be using arrows to represent forces. So that would be basically as straightforward as this. As simple as it is, it's important to understand why this diagram works for us when it comes to describing a vector-like force. You basically have two portions in this arrow diagram. You have the head and you have the tail extended behind. The head is there to represent direction diagrammatically because it's telling you where the force vector is pointing, right? whereas the tail and its length specifically tells you how large the force is or how small the force is. So, for example, even me, without needing to give you numbers, you can basically compare this force with this force. You can instantly say that, let's say if this is F1 and this is F2, you immediately recognize that F2 is larger than F1. And notice how you didn't have to rely on numbers, right? You just compared their lengths, or their tails. So in that sense, the tail refers to magnitude. So that's why arrow-based diagrams work so well for a majority of vectors, including a force, because it's this one concise, simple diagram that gives you an idea of both magnitude and direction simultaneously. Great. Now that we're dealing with vectors over here, it's important to realize that when it comes to a vector like a force, it's very rare that you'll ever deal with just one force alone, right? Again, think of that same box resting. I could, if I want to, apply a force in one direction, but I can imagine that there will be multiple other forces that could possibly act on it, right? Realistically speaking, that's the most plausible scenario. So then it's important for me to learn how I can basically combine multiple forces, right? That's a pretty important feature over here. So now the question is, how do we combine forces? Well, since all forces are vectors, it makes sense to then claim that forces can be combined using the rules of vector addition. So here we're not dealing with just numbers, we're dealing with numbers, meaning magnitude, as well as the direction. So we will be diving into the world of vector addition now. And we'll keep things straightforward for the most part for this case, and we'll start with the simplest kind of vector addition, that is forces that are being vectorially combined in one dimension. And then we can build complexity from there. But first, let's see how we can combine two or more than two vectors in one dimension. So I repeat, we're dealing with vector addition for forces. Let's specify ourselves to that. Vector addition for forces in one dimension. Now I remind you that one dimension basically means along a straight line. Along a straight line. So that could be horizontal, vertical, even diagonally, as long as the other forces that are involved are along that same line. For the sake of brevity, I'll be sticking to just the horizontal direction. So let's begin with simple scenarios. And what I'll do here actually is that I'll consider scenarios where they're not just diagrams on a page, but something that you can picture. And so here we'll be not only dealing with numbers and arrows on diagrams, but we'll try to make it as physical as we can. So let's suppose we have level ground over here, and we have this box resting on top. And then you have Tufi standing here. Start. Now Tufi applies a force F1 towards the right. Now obviously we can imagine that the box will start to move along that same direction, suppose with some velocity v. Now imagine Dr. Sal stands right next to Tufi, and suppose he helps out. He helps out by applying another force in the same direction, F2. Now the question is this: will this box speed up physically or will it slow down? Think about it. Well, in this scenario, since Dr. Sal is basically helping out Tufi in applying a force in the same direction, there is a reinforcing kind of an effect wherein we can imagine that the box will actually speed up. So what this means, so this physical effect of the object speeding up, what this means conceptually, or what this means mathematically, is that there is this reinforcing or this additive effect among the forces F1 and F2 when they're directed in the same direction. So there is an additive effect, I repeat. So there is an additive effect start. So I repeat, there is an additive effect when forces F1 and F2 are in the same direction. Now this combined effect I can represent through the resultant force Fr, which would be simply F1 plus F2. So that's our first conclusion, that when forces are arranged in the same direction, there is an additive effect that we see physically, which we can represent as basically a sum of F1 and F2. Great. Now let's look at the next scenario. Now let's suppose you have the same level ground, the same box resting here. You have Tufi once again applying a force F1 towards the right, which causes the box to once again move towards the right as per usual. Now let's suppose Dr. Sal, instead of helping Tufi, actually goes in the opposite direction, and instead of helping out Tufi, actually resists Tufi by applying a force F2 in the opposite direction. Now what do you expect to happen physically? Think about it. Well, now, since Dr. Sal is resisting the effect that Tufi is trying to create in the box, there is basically going to be a cancelling or a reductive sort of an effect wherein we expect the box to slow down. So instead of speeding up, the box actually slows down, which represents a reductive effect. And this reductive effect occurs when F1 and F2 are in the opposite direction. So notice how it's the same forces F1 and F2. There is now a different physical result entirely, simply because we've arranged the forces F1 and F2 in opposite directions. So now when it comes to numerically representing this reductive effect, it's a matter of simply subtracting F1 and F2. Now, when I talk about subtracting F1 and F2, I could do that in basically two ways, right? I could write this, or I could write this, right? So then the question is, how do I know which one to write when? Well, the answer to that is, it depends. Why does it depend? It basically depends on the values of F1 and F2 and how are they arranged. This will make more sense when I present the simple example. Suppose I have this box. I have 10 newtons towards the right and 5 newtons towards the left. Now when you write its resultant force, you'd basically be inclined to do 10 minus 5, right? And you get 5 newton. But we remind ourselves that a force is in fact a vector quantity. We had written it over here. So since a force is a vector quantity, this numerical value isn't enough. You need to present its direction. So just based on the diagram, we can kind of guess what would the direction be, right? Clearly you can see that on this box, you have 10 newtons towards the right. This 10 newtons towards the right is much larger than the 5 newtons towards the left, right? Because of which, you can basically picture this as the 10 newtons overpowering the 5 newtons. So that if you were to imagine this in your brain, you would imagine that the box's, you can say, net effect would be the object moves towards the right, simply because you have the larger force overpowering the force in the opposite direction. So both in terms of physically and mathematically, you can say that the 5 newtons is directed to the right. And then you can imagine the opposite would be true if you had 10 newtons towards the left and 5 newtons towards the right. Then you'd have the same resultant force 5 newtons, 10 minus 5, but this time it would be directed towards the left. So how do you choose which one to subtract when? It's basically a matter of placing the larger force and subtracting the smaller force from it. It's just that you should in the end remind yourself that the resultant force will always be directed towards the larger force. So I repeat, in fact I'll write it down here, both points. The first point being that writing F1 minus F2 or F2 minus F1, it ultimately depends on which force is larger. So if F1 is larger than F2, you'd be inclined to pick this. And if F2 is larger than F1, then you'd be inclined to pick the second expression. The point to follow up after this is that the resultant force always points towards the larger force. Right? So now we've established two very important points in regards with vector addition for forces. In one dimension, when forces are arranged in the same direction, we add the two forces together, and whenever forces are arranged in opposite directions, we subtract them. Now let me present a third scenario, which is, consider this as a special scenario or a special case, if you will. Suppose you have this box right here. And now you have in one direction you have the force F, and imagine in the opposite direction you have the same force but in the opposite direction. Now if you wanted to write out its resultant force expression, you would basically follow what we just studied. Forces in the opposite direction, we subtract them. So F minus F, and this ends up giving us 0 newtons. Now the question is, what does this 0 newton mean? Now physically speaking, 0 basically means empty, right? Nothing. So 0 newton means that you're basically applying no force on the object effectively. In other words, you're basically creating no effect on the motion at all. So in other words, 0 newton resultant force means that motion stays unaffected. Now when you claim that motion stays unaffected, what happens after ultimately depends on what the object was doing before. If the object was stationary before, it will continue to stay stationary, since motion is ultimately unaffected. Or if it were moving with some velocity before in any one particular direction, then it will continue to move with that same velocity indefinitely. So I repeat, when you claim that motion is staying unaffected, the object will either stay stationary or continue to move with constant velocity. What we've expressed in all of this discussion basically is a very important law that we study in dynamics. This law is so important, in fact, that even Sir Isaac Newton himself notified or worked on this, and in fact called it Newton's first law of motion. Newton's first law of motion. So what I've described over here, let me present this more formally as follows. What Newton's first law of motion states is that when the resultant force acting on an object is 0, then the object maintains its state of rest or constant velocity, or you could say motion as well. So I repeat, what Newton's first law of motion claims is that when the resultant force acting on an object is 0, then the object maintains its state of rest, meaning it stays stationary, or continues to move with constant velocity. Right? Now this is quite important in the laws of motion that we'll study later on as well. But here I'd like to raise a question that seems quite abstract when asked first, but it's very important for us to link it when it comes to physics and all the objects that we have in this world. Now, when you talk about the second half of this statement, the object maintains its state of rest or constant velocity or motion. Now, when you picture this, it's not as if the object has a mind of its own where it can maintain some particular state of rest or motion, right? It's not as if the object has a brain with which it can decide that, okay, now I won't move, now I won't change my direction or something like that, right? So then the question we must ask is this: how come an object can maintain its motion? Is there some built-in property perhaps because of which it can basically resist any changes in motion and then only maintain whatever state it has beforehand? Well, it turns out there is indeed that quote-unquote built-in property. That's what we call inertia. So let me first define what inertia is before I explain what it means physically. So inertia can be defined as an intrinsic property, meaning a built-in property, because of which objects can resist changes in motion. So this is the one physical property because of which any object, once moving or once stationary, keeps that motion indefinitely, especially when there is no resultant force acting on the object. Now, as again, I understand this is pretty abstract at first, but you can understand it pretty clearly when you picture it in relation with mass. So before I go any further, let's actually think of a thought experiment right here, and I'll draw it out as well. Suppose you have Tufi standing here, and suppose someone launches a tennis ball at Tufi with some velocity, let's say 1 meters per second, right? Or let's speed things up a little bit. Suppose it's 10 meters per second. Now sure, it might be quite fast, but Tufi will be able to stop it, right? A tennis ball isn't that massive where it could be difficult to stop, right? So we can realize that a tennis ball being smaller is easier to stop for Tufi. But then imagine, instead of a tennis ball, there's a massive boulder being thrown at Tufi, and perhaps it's being thrown with the same velocity. Now, despite the same velocity, a boulder is going to be much harder to stop for Tufi, right? No matter how powerful he seems, because of the sheer mass of the boulder itself, right? So then that puts into perspective that while a tennis ball is easier to stop because of its smaller mass, a boulder becomes harder to stop. Why? Because of its larger mass. So now we're presented with this general understanding that the more mass an object has, the harder it is to stop, and the smaller the mass is, the easier the object is to stop, right? So what we've concluded here is this, that the larger the mass is of an object, the harder it becomes to affect its motion. Whether that be slowing down a moving object or starting the motion of some kind of an object, no matter what. Whatever kind of effect you're trying to bring, it will be harder to do so for an object that's heavier or an object that has a larger mass. Right? And vice versa would be the case if you had a smaller mass. A smaller mass is basically one object wherein you have, basically it's easier to affect its motion. So what we conclude from an object that has this property wherein it's harder to affect its motion, that basically means that an object with a larger mass has more inertia, meaning more of an ability to resist any changes in its motion. More mass means more inertia. Whereas an object that's smaller or has lesser mass means that it will be able to resist changes in its motion fairly easier. So there's little to no resistance is what I'm trying to say. And so there will be less inertia. So in conjunction with mass, we realize that the more mass an object has, the more inertia it has, and vice versa. And so there seems to be a direct proportionality between the two. Now when you present this kind of a scenario, it becomes really easy to understand the physical aspect of inertia. Why? Because mass becomes a physical manifestation of inertia. And this is a very important point to note down. That before this, you might remind yourself that okay, a mass is nothing but the amount of matter in an object, right? But when in relation with inertia, it's very important to describe mass as a physical manifestation of inertia. And we've already seen why. Because when you have an object that has mass, and let's say it has more mass, then that means that whatever force you apply on it, it will resist any changes in its motion a bit more than other objects with smaller mass, right? Which means just by knowing what mass it has, any object, then you instantly know how will it respond to any changes in its motion. Will it resist more? Will it resist less? And so you can picture inertia better by having a better understanding of mass, beyond it just being the amount of matter in a body, but rather a physical manifestation of inertia. Great. So up to this point, we have basically covered all the nitty-gritty details of the first law of motion, where before this we had introduced force, the concept of force as a push or a pull, it being a vector quantity. We saw how forces can be combined in one dimension, wherein forces in the same direction add up, forces in the opposite direction subtract. From this, we were able to introduce Newton's first law of motion, where we claimed that when there is no resultant force acting on an object, then the object basically maintains its state of rest or constant motion. And from there, we were able to derive another intrinsic property that objects have, that is the concept of inertia. This intrinsic property because of which objects can resist changes in motion. Moreover, we were able to conclude that mass and inertia are directly related, so much so that mass becomes a physical manifestation of inertia. Great. So next time we'll extend our discussion from here and dive further and further into all the other subtopics of dynamics. Thank you.